Thank you very much. So I will talk about clocks. We've heard a little bit about them today, and I'll mention a number of them, but keep in mind I'm an expert on one. So watch on the glycan side, and I'll name all the experts on the others. So first, why should we measure biological age? Why would we need this as a marker? Well, we know that chronological age is not a good enough measure of health. All of us, and I'll give you 2 examples. We recently tested a number of centenarians in Costa Rica, and there were 101, 103, 105, and none of them actually had any diagnosed condition at that point, none that we can diagnose with traditional healthcare. And they're already achieving extreme longevity. Well, on the other hand, we have friends, I have a colleague who started working with a company when she was 19, but at 16 she got a diagnosis of rheumatoid arthritis. Then at 20 she got a diagnosis of MS, and she has a life expectancy which is greatly reduced to where she is living. So biological age should give us a better indication of health than chronological age, and also this risk of disease and mortality, especially in people who are not aware of it, or younger individuals who have this accelerated risk, but it's going underdetected. And aging clocks have been a mission for a very long time. Actually, the first assumed biomarker of systemic aging were telomeres. But then we learned that telomeres are a really good marker of aging of a single cell, but they're not as good of a marker of aging on a system level, because we have cells, trillions of cells with many different ages. So if we collect a sample and try to calculate an average age, it doesn't equal a very good systemic age. And for systemic age, now we have 2 very good candidates. So the first molecular systemic age clocks were the glycan clock and the Steve Horvath DNA methylation clock. And by complete coincidence, they were published on the exact same date in 2013. So last year we celebrated their 10th anniversary, and the first glycan clock was developed in Croatia, and Steve Horvath, who's the inventor of the epigenetic clock, his surname means Croatian. So we decided to hold a conference in Croatia to celebrate their anniversary. And if you Google, actually I have a link on the other page, we can share it with you afterwards. You can see all the recordings if you look for the Longevity Symposium. And Steve, so the epigenetic clock inventor, he was actively looking for aging, looking at the epigenome. We were not looking for it. We stumbled on it by complete random coincidence, by looking at a molecule that's mainly neglected in research, and we didn't have a lot of tools to look at it at scale in the past. In fact, our lab pioneered high-throughput glycomics. Back in 2007, we analyzed the first 1,000 human glycans together with a lab in Dublin led by Nikolina. And to date, our small lab or our research institute in Croatia looked at 85% of the total human glycome. We generate 85% of high-throughput glycome studies globally. And this is a review paper by Chemical Reviews. So these are just published glycomes. Out of 191 published glycomes, our lab generated 160,000 of those. And we did this in collaboration with all the top universities from Oxford, Harvard, pretty much everyone. And we found that when you look at these large cohorts, you see aging. Especially on IgG glycans, we would see that certain structures would accumulate with age and other structures would decline with age. And if you see on the graphs here, if I can only figure out a clicker, women are red, and they have a very different aging curve to men. Men have a very linear path, and in women we see this acceleration that's linked to menopause. And I'm going to get into that a little bit later. So then we were curious, can we see this aging in every population? And together with the Human Glycan Project, we looked at 27 different populations around the world, 100 individuals in each. And we saw that this prediction that the glycome would associate with the expected lifespan, but actually the strongest association was development index of a country. And we had a replication cohort in the UK of British minorities, the separate cohort, where we got samples from the first and second generation of British minorities, Indian, British, Caribbean, and Eastern European white. And we saw that in the first generation, their glycans would look like their original country, but in the second generation, their glycans would start to be more similar to white British, despite the ethnicity. So there's a very strong impact of environment that goes beyond ethnicity. And a number of these clocks are good predictors of mortality and morbidity. So the key thing they have to do, if you have an accelerated clock, does it predict disease and does it predict mortality? And this was a nice comparison done by Riccardo Marioni on the Generation Scotland Biobank, where he looked at if you have an accelerated glycan age or a Grimm age or other epigenetic ages, how does it predict diabetes and how does it predict all-cause mortality? And interestingly, although our clock is not modeled on mortality like the Grimm age, we were equally predictive of all-cause mortality as Grimm age. And pheno age, which encompasses clinical biomarkers, was less predictive than Grimm age and glycan age in predicting diabetes. So they are more predictive than some of the traditional markers we have. And maybe the most interesting finding we've had in the recent years is that these clocks don't, well, the clocks correlate because all of them correlate with chronological age. But if you look at acceleration in these clocks, epigenetic clocks and glycan clocks are on an opposite spectrum. We do not correlate at all, which is very interesting because both clocks are predictors of mortality and morbidity. Which means that aging is not one thing, it's multifaceted. There's a number of different mechanisms driving it. Maybe the most, something that Steve Horvath did recently, he developed a clock to predict maximum lifespan in humans. And then he tried to correlate that clock with his clock to predict mortality and morbidity. And these clocks didn't correlate, which means whatever governs our maximum lifespan is very different to what kills us before we get there. And that's one of the key things we're focusing on, but it also means that there's different theories of aging. Like one is a program. If we reprogram it, can we extend maximum lifespan? Maybe, but also we need to fix the things that kill us in between. And that's the part that we're focused on. Now then there was an idea that if we connect all of these different omics, we will develop the ultimate aging clock. And that was done in Edinburgh with the Orcadas Biobank. They looked at all these different multi-omic aging clocks and connected, in one case here in the middle, created a multi-omic or a mega-omic clock. They put them all together. And the pluses are prediction of hospitalization. And you can see in this ultimate clock, there was zero prediction of health outcomes. It basically became the perfect measurement of your chronological age. So putting these things together doesn't work. We have to look at them independently. And these are potentially very early mechanisms of disease that start with aging itself. But they're not one thing. And different clocks predict different things. But there are clocks which are stronger at predicting mortality and morbidity. And if I tell you that glycans are a great biomarker for this, I would be very biased. But when somebody else says it for us, then we can just agree. This was 10 years ago, this was a theory. But now we have more and more independent data coming out of how important glycans are. And this is a paper in preprint that's just about to be published in Nature Communications, done in Wei, Cornell, and Doha, where they looked at over 6,300 molecular traits and which ones of these would associate most strongly with age. And out of 20 associations, 9 of these were glycans, and the rest were predominantly sex hormones. Then this is a study which is being published in a couple months' time, but we have some data from it, where we looked at acceleration of aging on an individual level, because everything before was cohort level. So if you look at individual level, these are 600 twins followed over 30 years in Karolinska Institute in Sweden. And on an individual level, we see this very high prediction of mortality and also incidence dementia. So aging clocks on an individual level, particularly the glycan one, are very important for your future health. And the hallmark behind our clock is inflammation. Inflammation is a very old aging theory. It was published on all the way back in 2006 by Claudio Franceschi, but only recently we added it to the hallmarks of aging, although it is connected to a number of them. And we know that this mechanism leading to many different diseases has a common cause, and inflammation is part of about 3 out of 5 deaths globally or conditions connected to it. So we know it's important for the health outcome. But can we measure it? And here the problem is the same as we have with all disease. We walk into it blindly because our clinical markers are designed to detect disease when you're symptomatic, when the problem is very apparent and it's severe. Well, actually, we know that these chronic conditions start decades before we can currently detect it. And the markers we use for inflammation are doing the same thing. CRP, interleukins, all of this is when there's already a severe problem. Well, this, we call it sterile systemic inflammation, is far harder to detect. And we don't really have many biomarkers to do so. Well, we have a biomarker that does it, but it's not yet popularized, let's put it that way. This is why we go to all the conferences. We try and preach about glycans, and hopefully somebody reads the research. But glycans are this very neglected, and I've just realized these are my old slides, but that's my fault for changing them last minute. But the role of glycans in biology is to enable multicell life. They've evolved since we become multicellular. They're a way that we change our function in biology without needing to change our genes, and without needing to turn genes on and off for epigenetics. We can real-time add function to our molecules through glycans, who would incorporate all those genetic and epigenetic influences and connect them to what's happening in our environment real-time. So although you're not familiar with them by name, you are familiar with them by process. For example, our blood groups are defined by glycans. All of our immune communication happens through glycans. Cancer would use glycans to disguise itself to evade our immune system, and even conception happens through glycans. Sperm would coat itself in these healthy-looking, these anti-inflammatory glycans to evade the woman's immune system. So they're present in every process we have since we're multicell, and often they get confused with something called glycation. And glycation is this random damage to a protein by sugars or the food we are eating. And it's not a regulated or enzymatic process. Glycosylation, or what we measure where we see this more immune aging, is enzymatic. It's regulated. It happens within the cell when the proteins are being developed. And majority of proteins and lipids are glycoproteins and glycolipids. We also see that glycans change in a large number of diseases in specific ways. So if you look at the curve of this circle, each one of these little, like the G1, G2S, represents a different glycan and abundance of it. And you'll see that different diseases have different glycosylation signatures. So although we are looking at systemic inflammation, it is quite specific when we look at the details of what glycans are doing. And we see that these changes in disease resemble aging, where you can have a young person with a diagnosed condition who has the same profile of a healthy old person who has no condition. So it's present both in disease and aging. And if we go down to detail, particular conditions would be particular signatures will be predictive of certain diseases, and they have a quite high AUC, meaning accuracy. So for example, in hypertension, just by looking at glycans, 98% of the time, we can predict somebody developing hypertension 6 years ahead of time. In rheumatoid arthritis, just by looking at certain glycans, you can predict a diagnosis 10 years ahead of time with 92% accuracy. So they will in the future become clinical biomarkers that we apply in medicine to tell you you're heading towards a problem, but they are modifiable. So they're not fixed like our genes. For example, here, the signature we see predicting cardiovascular disease responds to physical activity. And in women, this signature is very heritable. It's 70% heritable, and we still see significant response to physical activity. So this is a modifiable risk. For diabetes, the signature we see predicting insulin resistance in diabetes responds to caloric restriction and weight loss. So we can tell somebody, hey, you're heading towards this problem in 5-10 years' time. It's time to do something about it now, before you actually get to a diagnosis and you end up on a drug for the rest of your life. And then, how do we apply them to the individual? So if we do something exciting in science, it doesn't always apply to the individual. So does this apply to the individual? And we have this evidence now. We've been tracking people longitudinally for decades. And this is one example of Mike Schneider from Stanford, who's tested himself 200 times over 10 years. And you can see how his structures are slowly changing with aging. Some are going up and down. And then you have 2 events of age reversal. One is linked to a lifestyle change, physical activity, running. The other one is linked to a diabetic drug, not metformin. So you can see how stable it is and then how well it responds with intervention. And in the case of Mike, we use the scientific method, meaning the analysis is run once. So you see a little bit of noise, but it's 1 to 3%. In the commercial method, we do triplicates, meaning that our error margin is less than 1%. So change in 1 year is a meaningful change. And you can see this is a woman's example. Women have different challenges to men. For example, pregnancy. So we see accelerates aging by 10 years, but you can fully recover. And in this case, she was heading towards Hashimoto's, but didn't have significant symptoms, so she managed it with diet. And when she reduces her fasting, she actually sees beneficial change, and her labs go to normal. And what activates the changes for her is stress. When she's stressed, she doesn't eat throughout the day. And we've tested many different interventions on how you can change your glycans and glycanage. I can't talk about, we won't have time, I only have a few minutes. But I'll highlight a few with a few warnings. There's no drug that has an effect in everyone. In fact, I'll switch to this. 20 years ago, Dr. Alan Roses said that majority of drugs don't work, or 90% only work in 30 to 50% of people. And we've applied this principle in healthcare, but we haven't really applied it in preventative care. And the word of caution is metformin. We have seen that in individuals, metformin has a significant effect. And this is an example of Tim Spector, who's been tracked for 10 years. And you'll see that he has a drop with metformin, which continues to stay there while he's on the drug. But then when we did placebo-controlled trial with healthy overweight individuals, we only saw effect in 1 individual, or 10%, which wasn't significant. And then when we tested the same drug in diabetics, we see 50% of people respond. But diabetes, only 10% of the population would develop diabetes. There's another condition, or natural event, that will happen to 50% of the population, and that's menopause. And this age acceleration that we see with menopause is equal to the changes we see with disease and aging. And we do see that this can be rescued with estrogen. This is a placebo-controlled trial with estrogen, and you see significant effect if you replace it, and you see accelerated aging if you don't. Of course, when you look at it in a non-control environment, so this is within the clinic, majority of women are improving, but then you see 2 people or 2 women going the opposite direction. And that's the case with every drug. It never works for everyone, even if it works as a general rule. Although I think estrogen is the only drug where we have hard evidence to say that it is a life extender. And this comes from the UK Biobank. They looked at 406 commonly prescribed drugs, and they identified 14 that prolonged lifespan. And out of these 14, 4 were estrogens. And this is actually a response to a joke. So Steve had a conference last year where he said at the end of the conference, he'll tell us a joke. And at the end, the joke was, the best thing you can do for your longevity today is be a woman. And then a few months later, I came to Steve. I was like, Steve, I think we can improve your joke. And this is a cohort from Worcester University. It's a HIV biobank followed over 10, 15 years. And they look at glycans, and they've had a small cohort of individuals born at male who transition into women and go on straight estrogen. And interestingly, they had a follow-up where they see a change in the health outcome, which was less coronary plaque. So the hardest form of evidence we need with a new biomarker is that if you alter the biomarker with intervention, it changes the outcome. And that's what we have here. You alter the biomarker, it changes in an anti-inflammatory way, and you change the health outcome. And this is the only evidence we have for an aging clock to predict an outcome in this way. But so the joke is, the best thing you can do for longevity today is maybe transition into a woman. But I doubt that many people will. So there is an alternative. And we see that actually the beneficial effect of testosterone is mediated through estrogen. So if you block testosterone entirely in men and you give it back, it's only positive if you allow aromatase. If you block aromatase, then it is pro-inflammatory. So this beneficial effect is mediated by estrogen. And to end, if you agree that the future of healthcare should be personalized and it should be preventative, we believe that glycans can unlock this future for us. They incorporate all of our unique influences from genetics, epigenetics to environmental influences. They help us evaluate on an individual level if something does or doesn't work. And they also help us preempt disease up to 10 years ahead of time. And that's it. Thank you.
Thank you, Nikolina. That was fantastic. I think Nikolina is also doing a fundraising round, and some of you may know that women only get 2% of all venture capital funding. So if you're interested, please find her. Now, in the meantime, it'd be great to have some questions for Nikolina. I'm sure some of you do have questions. Any questions for her? Professor Dennis Noble. Nikki, could you?
I can shout. The demonstration that glycans are a better predictor of disease over a 10-year period is extremely important and obviously needs to be looked at extremely carefully. And the reason I suggest that is that the study done on polygenic scores as a prediction of disease have been exceedingly disappointing. They were published by Hingorani and his colleagues in the British Medical Journal just last October, and for the two big killers, cancer and cardiovascular disease, the predictive ability of the polygenic scores is close to zero. Shocking. So, people are going to be examining what you're claiming very carefully, because if what you're saying is true, it will change the way we look at predictive ability fundamentally.
100%. And so I didn't have time to go through a lot of data here, but of course these are all research candidates, and the research has been going on for 15 years, and we probably need another 15 to get to where we want to go with any of these biomarkers. But we have shown in a mouse model that if you alter glycans in the hypertension prediction, we start with correlation, then with retrospective, then prospective trials, and we've gone to an animal model where if you change these glycans, you actually change the disease. So we had a model of obese mice, where if we give them a certain glycan precursor, they stay obese because of the diet, but they don't develop hypertension, versus the one that the control that does. So at least in animal models, we can show that this is actually a mechanism of disease. Now we need to do the same in humans, and I really hope that this field expands, because glycobiology is so small, and we can only do so much as one lab. So we really need a lot more of the world looking into it so that we can get to its full potential.
Thank you.
Any other questions for Nikolina? No? Okay. All right. Well, Nikolina, thank you so much.